So when the system is small, like 3.2
So in this presentation, the outline of my presentation as follows: introduction, then followed by motivation, then some tools, then foundation of fractional derivative, then Grunwald-Netnikov derivative, then after that Riemann-Leibniz fraction derivative, finally capital fraction derivative. Only the way of deriving the solution, way of presenting the derivative integral, only we have to see. See, this is we may call this history of fraction calculus. Yes. See, the differential equation and differential calculus started from 1671. This has two classifications. One is ordinary differential equation, and another one is fraction, partial differential equations. We know very well. Okay. See, I have a function f of x. Now I want to differentiate that. Then I am able to fix f dash of x or d by dx of f of x. Suppose in between some derivative with half derivative is there, then what is the value of that? So we all know very well d by dx of x square is 2x. Then if I ask d half derivative of x square, then what will happen? We are going to check. So these are only basic things we are going to check. So this is the birth of fraction calculus area. In 1695, the letter from L'Hopital to Leibniz, in the derivative, instead of n equal to integer other things, if n equal to 1 by 2, what will happen? That's the question raised. Then we need to think about new topic, that is fractional calculus derivative. So this is the birth of fractional calculus. It is 1695. For learning fractional calculus, for deriving the solutions or deriving the derivations, everything, we need some basic tools. The very important is factorial, n factorial. Then another one we need to use is gamma function, gamma of n equal to integral routine. Then the properties of factorial also we require. Gamma of n plus 1 equal to n factorial. Gamma of n plus 1, n gamma n also we are using. And gamma of 1 by 2 equal to. These three are very, very important for getting very basic, for example, half derivative of x. We are going to use these things. So the formation, so my talk title also like it is a journey from integer or fraction. So everyone, they are learning the basic things based on fraction derivative. They are going to start from integer order. Deriving the solution or derivative based on fraction order also started from integer order. So I start with y equal to f of x power n. So I am considering a polynomial function. So we all know very well the first derivative of x power n is x power n minus 1. So you differentiate, then use the idea I told you, like factorial idea, n into n minus 1 x power n minus 2. I am multiplying divided by n minus 2 factorial. Then I am able to write the first one is n factorial, the denominator is n minus 2 factorial. So I am multiplying divided by n minus 2 factorial. Then x power n minus 2 minus n. Then very quickly I am able to write the next derivative, third order derivative. It is n factorial by n minus 3 factorial x power n minus 2. Suppose I am going to take n, let's say value then n. Then it is I am taking k. So my derivative is d power k. Y divided by x power k is n factorial by n minus a factorial. N x power n minus k. Now, so up to now it is only integer order. Now I am to fractional order derivative. To check here, I am replacing k by alpha. Alpha equal to alpha belongs to R, but I am particularly considering alpha equal to verifying our fractional order derivatives. So the property of gamma function. So already I told you the fraction, some gamma function property n gamma n, gamma of n plus n factorial, something like that. I am going to use one by one. So numerator no issues, denominator something is there. So I am using gamma function. I can write n factorial equal to gamma of n plus 1. Same idea. So that becomes n minus alpha plus 1 factorial. Maybe now it is gamma. Gamma of n minus alpha plus 1. Then I'm using, instead of d alpha y divided by x power alpha, I'm simply using capital D of alpha. So this is the derivative of x power n, fraction derivative. So we reach the question. I asked the question already. What is the half derivative of x? X square. We can apply. We have general formula. We have general formula. We apply some particular values for particular cases. So I'm going to apply n equal to 1 first. In the previous formula, you check here d alpha. I'm going to take this half. Then n equal to 1 I'm taking. That means x power n becomes x power 1. Yes, n power 1. N equal to 1, alpha equal to half. Then I'm able to reach my answer d half of x equal to 2 root x divided by 2 pi. See, we all know very well about differentiation of constant function is 0, but we can simply apply the same logic here. We never think like differentiation of half derivative of constant c is 0. There are many different kind of derivatives. Initially, it started from Kothri-Kalan. They derived one first fraction derivative of general function. Then what happened now? Solving part is very lengthy and it is difficult also. Then Riemann legally both together they derived one solution that looks so simple. Then after that, Capito also extended the same Kothri-Kalan inequality, and that is called capital fraction derivative. Suppose if you are going through any fraction order paper, it is not only based on differential. You can find applications of fraction calculus in neural network topic, fluid dynamics topics also. Because some of my colleagues they are doing their research based on this fraction derivative application with your neural network, so many places. So if you want to go through anything based on fractional calculus, so you have to recall these things. So this is a simple example, but we are going to derive the required derivatives. I told you know, Kothri-Kalan, Riemann legally, capital fraction, everything we are going to derive. So what's the fraction derivative of a constant function? We told you already, don't conclude immediately. We know very well about differentiation of constant. Derivative of a constant is 0, integer of it. But fractional calculus, you are not able to conclude very immediately. Now, for example, if you are applying Riemann legally, you are not able to reach 0. Suppose if you are applying capital fraction derivative, yes, you are able to reach constant derivative is. So those kind of things we have to check. So if I try to find in this general case, where we have this is Kothri-Kalan. I'm trying with x power 0, that is constant. I'm not able to reach 0. I got the answer 1 by root pi x. Fine. So in the similar manner, we know p of x given is x square plus 2x plus 1. Immediately we are able to tell p of x is 2x plus 2. But what about p does not half? That's the answer we can simply conclude constant values always fixed. So the derivative I told you already, Kothri-Kalan derivative we are going to derive. So again I started from integer order. So we know very well about f dash of x is limit x tends to 0. So f of x, instead of this you can start with f of x plus h minus f of x divided by h also. But I am very much comfortable with this, so only I am following this methodology. F of x minus f of x minus divided by h. Then second order derivative replacing f of x in the above equation number 4 by f dash of x. Then use the formula 4. Then we are able to reach the second order derivative like this. Then third order derivative. So I have 1, 2, 3. So I'm going to find generalization like summation format. Then I can extend the same with n top. So I extend the same with fn of x equal to limit x tends to 0, 1 by h to the power n. Then summation I introduce. So I am using minus 1 to the power j because of alternating minus. It is an alternating case. Minus 1 plus 1 minus is that. So I'm interested in that. Then if I take, I told you already, integer order derivative is there or integer fraction is there. We want to get fraction order. Then I'm replacing n by alpha. So I'm considering alpha is a fraction part. So f alpha of x. Yes, I'm replacing n by x. In the summation, you check j equals 0 to n is there, but we don't have any value for summation values for fractional things. So if it is n, it should be an integer value only we are going to use. Then some substitutions I'm going to use. Instead of ncj, alpha cj or alpha j, I'm replacing this value nc r formula. I'm applying n factorial to the r minus r factorial and n minus r factorial. I'm able to reach equation number 6. So that equation number 6, actually that equation number 6 is known as Grunwald-Lettiglow fraction derivative. That is the first derivative based on fractional. It is then maybe it is around 1710 here. Then we may do some as per our convenience, we are using n equal to x minus a big H, maybe x minus a minus 0 big H. Then a less than x I consider. Then I can do some simplification in the formula. Then I'm able to reach 7. I'm claiming this equation is Grunwald-Lettiglow. So you check the derivative, you check the formula. It looks a bit difficult. So we are moving to the next one. I'm simply going to extend the GM fraction derivative to Riemann-Leibniz integral. So I started again. I'm taking the NCR part, alpha CG part. I'm doing some simplifications. I'm adding, subtracting, multiplication, divided by something. I'm able to reach some kind of answer like this. So simple calculations only. Then you check here. I have f alpha of x. Now I'm replacing alpha by minus alpha. Then I'm able to reach integral. So 1 by t is integral will be alpha variable. So instead of alpha, I'm replacing minus alpha to reach Riemann fractional integral. Riemann-Leibniz fractional integral I'm going to reach. So it is the equation number 11. You check the first equation, f of minus alpha over x. I reached one answer. Then finally, I'm replacing f minus alpha by I alpha because of this integral. So I reached one formula that is called Riemann-Leibniz fractional integral. So equation number 11. So we may apply some simplifications. Finally, the known result integral. I'm connecting summation with integral because we check our formula. You check the last in the equation number 11. Summation is there. But I want to get integral because Riemann-Leibniz integral is based on integral limit 0 to r a to x something like that. So I'm using the connection from Riemann sum a to b f of x dx. We know very well if you are using numerical approach, then some kind of number of rectangles we are able to reach. So adding all the areas of the rectangles, we are able to conclude the connection between integral and the summation we are able to reach. Both are same. Then it is similar with the above thing. You check the last line, last part of 11. It is x minus j, but in the current here I have f of x plus j. So it is some connection is there. I'm applying the connection. I'm able to reach my integral. Yes. Check the last equation number 14. Doing simple calculation, we are able to reach I alpha of f of x 1 by gamma of alpha a to x integral a to x minus 2 alpha minus 2 f of u du a less than x. So this is for Riemann-Leibniz fractional integral. So from GL fraction derivative, I am reaching RL fractional integral. We are able to find many particular functions like f of x equal to x. If I have a constant, if I integrate the constant using this Riemann-Leibniz, if you are using fraction order alpha equal to 1 by 2, you are getting some particular answer for fraction order. Suppose you want to check the same with integer order, you apply alpha equal to 1, then automatically you are going to get the CX if it is constant integral, constant function is there. So if you are having x, if you are integrating, you are going to get x square by 2. You can apply the value here. You can replace f of u particularly if it is c. Everything it is there. See, what is a Riemann-Leibniz fraction integral of a constant? I am replacing f of u by c. Then I am able to reach the answer c x minus alpha power divided by gamma of alpha plus 1. Suppose if I take alpha equal to 0, I get this kind of answer. Fine. So this is a particular particular case, I'm applying some particular values. So those who are contributed in fractional calculus, you can find from 1700, some 1750 up to 2055. There are so many persons, they are contributing their level best in fractional calculus form. So this is the result. Just now we arrived Riemann level fraction. The properties are there. So then linear property, constant integration property is there. Then I told you already, what is the integration of x power n? Fraction or integration. One part a, one part x. That means the integral limit lower limit is a and upper limit is x. That alpha mentioned the value of fraction. So 1 by gamma of alpha. If you are replacing alpha equal to 1, then a equal to 0, then you keep x is same, then you are able to integrate. It is like exactly similar to your integer order. So this is fraction order x power n. Yes, I told you, you apply alpha equal to n equal to 1 by 2, you are getting x root x integration. So root of root by 2 is gamma function most of the cases for which the answers. So if you are replacing alpha equal to n equal to pi, we are going to this. Because one general thing we are having, that is Riemann-Leibniz fraction integral. Applying some particular cases, particular values we are able to use. If you want integer order, derivative, we are able to use. Integer order fraction in integral, we are able to we want we are able to use that also. So e power kx, yes, it is similar like integral e power kx dx. Suppose if my alpha is 1, I have to get the answer, yes, e power kx by k. If alpha equal to 2, it is double time integration by k square. Fine. So sin x, cos x, everything we are able to derive using the formula we reached. Suppose I have I power alpha, that is positive thing. E alpha is positive here. Suppose if I am replacing alpha by minus alpha, integration becomes differentiation. So your integral becomes derivative now, replacing alpha by minus alpha. So I am going to reach Riemann-Leibniz fraction derivative from integral. That's the thing we are doing. Yes, fraction derivative. So we are able to reach derivative from integral. So that's the thing available here. See, you check the first one, Riemann-Leibniz fraction. First one, Riemann-Leibniz fraction integral. The second one is Riemann-Leibniz fraction derivative. The difference between Riemann-Leibniz fraction derivative and the capital fraction derivative. Suppose if we are differentiating a constant function using Riemann-Leibniz fraction derivative, you are not able to reach 0. But if you are applying the same thing in capital fraction derivative, we are able to reach 0. So we are not going to say, we are not concluding Riemann-Leibniz fraction derivative is wrong and the capital is the only correct thing. No, it is one way, that is another. Which one is correct? So both are correct. So the derivative part is here. What is the difference? First you have to differentiate. First you have to integrate in Riemann-Leibniz. First you have to integrate, then differentiate. For example, 2 is there. If you are integrate, you will get 2x. If you are differentiating that again, you will get 2. So that is Riemann-Leibniz fraction derivative. But in capital fraction derivative, first we have to differentiate, then integrate. If you are having the same function f of x equal to 2, differentiate that will give you 0, then integrate, same thing. So it is happening here. That's the difference between these two. Fractional derivative of a constant function, I told you already, we are not going to reach 0. But the same thing you apply in capital fractional derivative, we are reaching 0. I told you the difference. So if it is x power beta, sir, how to identify a problem, a function is given, a derivative is given, how to identify whether it is based on RL or C? So you check lower limit I mentioned A, then X, alpha, then one C I use now. That C is capital derivative. In the place C I am using RL, that is Riemann-Leibniz. Only those two fraction derivatives are. There are recent times there are many fraction derivatives developed and many issues happen. So many comments, corrections are happening. Somebody they are claiming that some new fraction derivatives are wrong. Somebody they are claiming that that is also correct. Many papers published, many comments, many things happening. But up to now, only 3 fraction derivatives they have no issues. One is Riemann derivative. The second one is capital fraction derivative. Generalization of Riemann fraction, Riemann derivative, and the capital is Hilbert fraction derivative. So these three are up to now. These three are the most acceptable derivatives by all others around the world. But in some areas, in some European countries, they are claiming that some fraction derivatives that is called Akandano balloon derivative is wrong. Somebody they are telling that conformal fraction derivative that is wrong. No one is fraction capital and Riemann derivative also with the Hilbert fraction derivative. Those three derivatives are up to now it's 100% correct. Suppose you want to focus your research based on fractional calculus, then focus these three derivatives. So it is x power beta, it is similar kind of approach. We are able to reach answer like this. So hereafter, some other tools to derive the solutions I'm going to mention. Laplace transform, basic things we are going to apply based on it is the L of f of t. So I'm going to use some particularly the convolution theorem, so many things. So you have to go through this Laplace transform also. Suppose you want to learn fraction calculus, then this is most important thing. See, we all know very well about expansion of C x, sin x, cos x, binomial. See, one function is that is beta Laplace function. This is the one function you can derive all your required series like e power z, sin z, cos z, everything for this one dimension. So this is also most useful definition for you if you want to learn fraction calculus. Some particular things. It is two parameters, e alpha beta. Initially they derived only e alpha of x something. Then they they extended with the two parameters. They are including one more that is beta. So you are seeing in equation number 20, you are seeing e alpha beta of x. So this is the most useful function for deriving fractional derivatives. Conference on computational techniques organized by University. And this is a joint work of my co-author, in this paper, the aim is to address the challenges that we face while investigating the statistical convergence for the sequence of sets. Firstly, we will introduce the operators, namely delta x minus and delta x plus, applied on the sequence. And then we will apply the delta zero intersection property also to have some explanation of the statistically complex spaces. And we will also give a sandwich theorem-like characterization to those techniques. So let me explain the background a little bit. So, as documented by Zervati, the concept was first explained by Bechdel in 1902, but through the influential works of Kothri with wider recognitions, now known as Kothri-Kalan. Later on, Wiseman also made separate approaches to study of sequence of convergence, which is now known as Wiseman's convergence. So, as per Kothri, any decreasing sequence, this is to be noted, the decreasing sequence of subsets at the limit, which is the intersection of all the supergroups. But this is only defined for the decreasing sequence. So, can we go for any type of sequences? So, if we go for any type of sequence, say for set of singletons, sequence of singleton sets in usual topology. So, every singleton sequence. Will have the limit empty set until it's a constant sequence. So, but if we do sequence 1 by n, so 1 for n, the point C. So, similarly, the question is, does not the sequence of singletons containing the point 1 by n convert to the point to the set containing singletons in yes, so basically, so Wiseman introduced another concept of convergence for sets. According to him, any sequence of closed sets, this is to be noted that another closed set A, given that limit tends to infinity dx, x belongs to x, where dx denotes the distance between the point x and the set A, distance of the point x to the set A. So, with one example, if we explain the distance from the point 1 and the distance from -1 to the sequence 1 by n, singletons at 1 by n is reducing to 1. So, according to Wiseman, welcome 0. But the question is, can any type of sequence, say, excluding this closed specific for the closed sets. Another thing that is that if the factor absent, then this problem while investigating the statistical okay. The base of asymptotic density or natural density. For example, the set of even numbers have a natural density, and the set of hundreds have nation convergence for real sequences. One example. Realization of statistical convergence is the ideal convergence with base in that. So an ideal is a that contains the null set, which has the hereditary property and finite. Always use examples are IP. Finite subsets of natural numbers. I tell them that natural number that is in a case finite ideal. This so this is one particular example of IP convergence for reference. Today major approach so in 2012, Murray started another investigation on this, but that was also restricted to the sequence of closed sets. Now, some different approach was made by Inan et al. In 2015. That introduced two operators nx minus and nx plus, which are applied on the sequence of sets. And using those, they have defined ideal convergence. But the thing is that this is also restricted up to the sequence of closed. The question is, can we define in a way so that we can use it for any sequence of sets, not only for a specific. So these are some concepts related to statistical compactness. A topological space is called statistically compact. That has a subcover whose features collection of indices will have the natural density. Present compactness in terms of family of closed with finite intersection. Compactness it is being a delta zero intersection. The result says a couple physically compact even only if every family of closed sets as non-empty intersection.
we have introduced two new operator minus, which is actually collecting the sequence array, which for array is an empty set for u of n, and delta m I m naught. So, we verify its properties, we show that this one is the Morgan stack properties of this operators are very. So, product of sequence properties related to the functions. Uh, all those elements of the space X. The natural density of delta x might statistical limit infinite, and a similar if these two limits are equal, the limit is statistical. What not for
Thank you. Yes, sir.
Okay, next we welcome Ms. Nitisha Pandey, scholar VIT Bhopal University itself, for her work on higher order collaboration methods about the learning problems. Nitisha? Good afternoon to all the dignitaries present here. Myself, Nitisha Pandey, research scholar under the guidance of Dr. Tina Jain, SASL Department, VIT Bhopal University. Today I am presenting our work on 5 other orthogonal spline collocation techniques for solving periodic boundary value problems. So this is the outline of our talk. First we start through the motivation, then introduce our orthogonal spline collocation techniques, then numerical results, future trend, then end with references. The motivation of our work is to investigate a high-order orthogonal spline collocation techniques for boundary value problems. They have so many traditional approaches, but they have some limitations like slow conversion rate, heavy conversion cost, not effective for all types of boundary conditions, and unstable numerical solution. So we go through the collocation method as it has advantage like it is simply implement compared to the finite difference method or traditional method. Collocation prefer very fast calculation. Another advantage is like it is systematically incorporated boundary condition and interface condition. So this is the introduction part. So we suppose the PR polynomial and pi is the partition of the interval. Then we define the piecewise polynomial function where MK is the piecewise polynomial function where Ck represents the function which is k and continuously differentiable. Then we define another space MKRC which is our boundary condition space. Now this is the formula to find the dimension of these linear spaces. So here we define M13 which is denotes like C1 time continuous differentiable function with polynomial of degree 3. Then another space M130 which is our boundary condition space. And we use the monomial basis function. We choose 2-point Gauss. Now let's consider the second order linear differential equation with periodic boundary condition like equation 1. Then we choose the approximate solution by orthogonal spline method. Equation 2 is our approximate solution which has T as a degree of polynomial. So by the supercontinuity formula 2r minus 2 we get 4 as our rate. are our bases. These are our bases for equation 2. Now differentiating equation 2 times, we get equation 3 and 4. Now putting these on our original equation 1. For 2 points xy minus 1 and xy, we get a linear equation and we express this linear equation in matrix form. So as we have 2n collocation points and 2 boundary conditions, so we get 4n plus 2 nearly a block diagonal form, which is where dA and dB are the boundary conditions and A1, B1, C1 represent like this form. Now after solving this, we get our approximate solution. So for numerical result, we compare the result with the approximate solution with exact solution and estimate the maximum log error. And for the order of convergence numerical method, we compute this formula where U represent the exact solution and UHI represent the numerical computed solution with step size HL. Now we take example 1 for one-dimensional M2 equation, which is periodic boundary condition equation. We have parameter like this. And this is our variance is our exact solution. So we solve this by collocation method. UH is the approximate solution where I am taking 4 as a polynomial degree. So we get this as a rate of convergence. Now differentiating equation 8 2 times, we get equation 9. Here I am taking 3 collocation points A, B, C. So we are getting 3 linear equations. Now these 3 linear equations can be expressed in the matrix form. So as I have 3n collocation point with 2 boundary conditions, so I am getting 5n plus 2 block diagonal matrix. So the element like this, A1, B1, C1, D1. Now this is the result of cubic and quadratic basis. When I am using cubic basis, we are getting 4 rate of convergence for both and derivative of the solution. For quadratic, I am getting 6 rate for both solution and the derivative. Now this is the comparison result when I am comparing our method to finite difference method. So we are getting a minimized error as compared to the finite difference method, and also the rate of convergence is also observe the same, which validate our result. So this is the graphical representation of error where red line represents the finite difference method graph, which easily show that blue and green line represent collocation graph. So the error will be very high in finite difference method. And another graph is for rate. So as we increase the grid point, our rate will be fixed. Now this is our numerical computed solution and this is the exact solution, which both are same. Now second, we take Poisson equation for boundary condition. So this is the result for cubic and quadratic. For cubic, we are observe 4 rate, and for quadratic, we are observe 6 rate for both solution and its derivative. Now this is the comparison result for finite collocation method. Collocation method, we get a minimized error compared to the finite difference method. So this is the error graph. Red line also represents finite difference method, and blue and green line represent collocation method for function and its derivative. Another graph represents the rate, which is 6. So this is the numerical solution or exact solution graph, which both are same, which validate our study. So as we know, boundary vector problem or periodic boundary vector problem arise naturally in physics, chemistry, or engineering department, like wave equation, quantum particles, or heat conduction laws. By solving this collocation method, we get adequate solution with previous derivative, stable convergence rate, error reduction law, and easily handle discontinuity function too. In future, we study the convex analysis with error estimation in function space and extend this approach to high-dimensional problem. So this is the reference for our work. Next, I would like to call upon Mr. Amitabh Bhattacharya from Boston University. Please.
Good afternoon, everybody. When we look at the statistics, and he has also my topic for today is on synthetic integrated data generation using heuristic-based Bayesian method. In which I will, in my presentation, I will focus on non-heuristic. So this will be the outline. Coming straight to the what motivates is like in the industry, we always base the issue of sample size estimation based on limited data availability. And also, it is a problem getting access to the data due to patient safety and privacy issues that are normal in the industry. So, with the limited amount of data that we get, how can we utilize that data to come up with simulated data that could mimic the real world scenario, so that we can estimate sample sizes better? This has a huge impact because if we get the sample size wrong, it could mean that our trial is not powerful, and it is a huge loss of in terms of economic as well as patient safety concern. So how can we generate synthetic data which mimics the real time data? So historically, what has been done is based on available data, they find parameters like lambda or Q rate, and then based on that they come up with the data. But they have found that they have their limitations. So with new techniques, there are certain improvements, and also in certain rare diseases, utilize data availability from one or two studies, and using the methods, we can come up with synthetic data. So one difference of survival data is that it has a sensory component. So it is not like continuous or categorical data. And there are different kinds of sensory, right sensory, left sensory, that we have to deal with. So yeah, so I mentioned the synthetic data is due to the privacy issues, and using that we can do realistic simulation in epidemiological. So basically, when we have several data, like for example, say we have two example data sets, we are trying to see how close they are matching. So convex linear divergence is one way to check for divergence in two data distributions. But we see that it would not work that well in the active event data. There is an improvement in symmetric, like divergence symmetrics in Jensen-Shannon, but So, so we have found that alternative metrics that is based on Breer score, which essentially checks the similarity of the survival at given time point. That would work better for a time to event data set. So, so this is an example. These two lines are from two different studies that deal with the renal cell cancer trials. We have taken treatment sunitinib data from two different trials and checked how similar they are. And based on this, we want to generate the synthetic data. So we see that they are kind of similar, some divergence between the two studies. So we checked the convective divergence, but you see the result is negative, which means that it didn't work because the normalization did not add up to 1. J's did better, but both of them do not take care of sensor. So, but if we see the rate score based data, we see that over the entire period of 20 months, there is a close match between, say, after 2 months to 16 months in the area here. And this is the integrated score, which also kind of gave a good understanding of how close they are matching over time. We then generated this synthetic data, which is the blue line. But you see that blue line is based on some parameters like lambda. So based on the two data sets, the lambda was it generated a data set synthetic which is very different around the central part of the time period. So what we did is based on this Breer score, we separated out the data from 2 to 16 and then generated the data separately for these segments and then regenerated the synthetic data. Now here you see the blue line is kind of very close to the other two, the original data sets. So this is a good thing we feel that based on the Breer score can utilize and it is not computationally intensive. The Bayesian based methods have gained popularity. The Dirichlet distribution is nothing but the multivariate version of the beta. It sums up to 1. So we have to check two methods. One is the local sampling based, which is the local Dirichlet mixing, and we only use one data set, so it hasn't given the similar synthetic data. The red line you see is diverging. We also tried another way. This is the case of Dirichlet and the Dirichlet process, which has a base and the concentration parameters. We also use the Dirichlet process full mixture based synthetic. It did give us a good result, but we only used one very similar data set, so there is homogeneous data. So it has performed, but we believe when we include heterogeneous data, Dirichlet will do better local. So in this to reiterate that, but our alternative is when we have low data, we can, instead of the computationally intensive Dirichlet, we can look at the IPS and divide our data sets to get a more closely close synthetic data. To reiterate, the local Dirichlet method is better in heterogeneous data than the like the Bayesian or those methods are good when we have homogeneous data. So in conclusion, yeah. So just to give you some limitations, so we know that most of diagnostics are not well because they are not handling censoring that well. So we have to do more studies. The different level of censoring we have to make this medicine, okay? And currently our data is only not having high level. Like it would be better to use clinical data which has a lot of covariates in terms of probability, and then check how the alternate methods are performed. So we have just checked that the research method are doing as good as the like the standard Kaplan curve, which have limitations in terms of proportionality. So that part is done, but we have to solution. Thank you. Weightage to have the fixed family for the data. No, we do not have a fixed model. We just look at the base and then also we have this metrics where like the diversity metrics to check how close they are with the data. So in the statistically, we just have to know the parameters, say lambda, but then they would perform that well with high dimensional or the metric. Yeah. So we are just comparing with the standard Kaplan and
ये बोला था कि ये बोला या इसका अच्छा
I would like to thank all the participants to attend the session. And especially I would like to thank the scholars who are here with their new works, because they may be not knowing all the things about the field, but still they tried their best. All the best.
Thank you, ma'am, for gracing this event with us, your presence, and providing us with your wisdom. So may I now request our convenient Dr. Hekanta Kalenda to please felicitate ma'am with a token of appreciation. A huge round of applause. And of course, a special thanks to our organizing committee and volunteers who have worked tirelessly with mind, the scenes to ensure everything runs smoothly. Now, I request our convener, Dr. Hekanta Kalenda, to come up and felicitate them.
Okay, before feliciting, I'd like to announce one announcement.
from our offline participants. Of course, online is going on. So for the best presentations, Chiran, Monica, Sun. Okay? We have shortlisted your name. No, it's not final. Online is going on. From offline, we shortlisted your name. Okay? Now online is going on. From that, we compare, we declare other benefit program. Fine? And our lunch is ready by, and we'll come back around 2:15. We'll start our benefit program. Now I'd like to, yeah.
So firstly, I would like to call upon Mr. Lakshya Pandey to please come here and achieve something. I request Mohammed Sadiq sir to please come and felicitate our organizing.
Next, Spandan Agrawal. Next, Harshita Srivastava. Astana Gaurav. Ashutosh Yadav. Janvi Virao. Gaurav Sharma. On behalf of the core committee of ICNACT 2025, thanks all of the students organizing member. They are BTech students and they really in their hard work, and our 2 days conference successful because of this team only. Okay, I really thankful to you and thank you very much. Okay. Now we can proceed for lunch. Same menu.